Hi also from our side. Thanks for the introduction. So I'll just go ahead and quickly skip in. To give you some context, we've done a lot of development together with ABSTRACTIONS and UR, and also Picnic was involved in developing the whole ROS-II driver. It's all basically one ecosystem that fits together quite well. And in the latest development, we wanted to make some more improvements about getting things on more of an industrial grade, or not the grade, but like industrial customers would like to use the drivers to enhance some more of the features to make it more flexible, basically. So one approach was to couple the robot controller more closely to the ROS ecosystem. So I come more from the ROS development side, and as ROS developers, we usually like just to have some input where we can stream data and move the robot. And of course, robots offer a lot more than just that, and our aim was to combine those two worlds a little bit better together to gain more flexibility for everybody, basically. So I'll start with the new controllers that we developed. We had the Cartesian robot controller, scaled controller, and also a full trajectory forwarding interface. I'll briefly introduce them. The motivation for doing Cartesian controller was basically that, first of all, many people want to do Cartesian control. It's more intuitive to actually command Cartesian in Cartesian space, as you can imagine, a bit better than just the joint space. And many robot controllers actually support Cartesian execution quite well. They have an accurate IK, so you don't have to solve it on ROS side and rely on a accurate URF description of your robot, which we tackled with the URCAP driver before. So we do have an accurate URF description if you do the calibration, but some other robots might not. And so if the industrial robot controller provides that kind of interface, why not try to use it a bit more? Also, if we shift execution towards the robot controller instead of interpolating on ROS side and executing the trajectory, we first of all reduce the real-time requirements that are actually there for the ROS controller, the ROS PC. So there are controllers that command data with 2 or even 1 milliseconds, which raises some requirements for real-time control. And also, robot manufacturers usually put a lot of effort in actually making sure their controllers are optimal in some certain way, so that your drives live longer, execution times are optimal, and so on. And so the idea was, why not benefit from this knowledge, basically. To give you a short overview, this tells us the different components involved in this. All the colored components are components that were recently developed. So on we have the user interface side, where we basically created a new interface. We have a couple of new controllers and also hardware interfaces, which I will go briefly into during the next slides. On the interface side, we basically implemented 2 Cartesian interfaces. We have, first of all, the geometry twist input. So similar to how you can directly command joint velocities with existing controllers. So now you can command a Cartesian twist for the TCP, for example. And we created a Cartesian trajectory description, or Cartesian trajectory execution description, basically, which was together with the community developed in a nice feedback loop. So many of the people here in the audience also contributed to that. So I think this is quite a nice outcome. Then on the hardware abstraction side, we have a couple of new interfaces to actually speak to the robot. So we have this twist command interface to actually send a Cartesian twist. We have a trajectory interface to send a whole trajectory down to the robot in Cartesian space. We have a joint trajectory interface to send a complete trajectory interface for execution on the robot. And then we also have the post command interface, which is similar to the position joint interface, basically. And the idea of the trajectory interface is really that you send a complete trajectory to the robot controller and let it handle execution, so you don't have to do interpolation and commanding set points at each time cycle on your ROS machine. I'll come to that later in the controllers that we actually developed. So these are those 3 controllers, basically. We have the twist controller, which is basically just forwarding any Cartesian twist that you give it on the input to a twist that gets sent to the robot. So this is, for example, very useful if you're doing some visual servoing or post following, so you don't have to do any IK or anything on ROS side. You just take the difference from your target pose to your actual pose and amplify that to some kind of twist as you like, and you can send that directly to the robot, so you can do really reactive motions where you don't have any conversion in between, so it's also quite reactive. That was the main target of that. Then we have the path-through controller. It's actually path-through controllers, as one for joint space and also one for Cartesian space, where the interface is the same as for the existing joint trajectory controller and also for the new Cartesian trajectory controller. So from the outside, it doesn't really look any different to the traditional joint trajectory controller. However, execution is shifted towards the robot controller to let it care about that. And it also, as it's being executed on the robot controller, it currently also supports blending at waypoints, for example, as you're used from a more industrial application point of view. However, currently we're also working on actually doing some spline interpolation on the UR robot controller, so that the execution of joint trajectories will be very, very similar or even kind of the same as you would do with a traditional joint trajectory controller, but executed on the robot controller, which then reduces the requirement of having a real-time loop on the ROS side. So you can reduce the control frequency basically a lot. Do you still see the slides? I hope so. That might work. Perfect. Sorry, Rune's PC just lost internet connection. You still see the slides, I hope?
Yes.
Great. So the question is how to integrate this into your existing robot driver, as it was all developed with the robot driver in mind, and it's integrated into your robot driver. However, we explicitly wanted to sign this robot driver independent. I mean, it's just ROS control extension, so you can include it in every existing ROS control driver. You just have to implement a couple of hardware interfaces, as I've described before. Depending on the interfaces that should be implemented, there has to be some code written on the robot as well, especially for the trajectory interface, where you have to integrate the trajectories coming in. And if your robot does not support any Cartesian interfaces natively, however, you would like to offer the Cartesian interfaces on the ROS side, there's also a joint-based backend as a fallback, so you can have a Cartesian trajectory controller that then uses an IK to go back to joint space, but on ROS side. And that IK is actually also plugin-wise exchangeable. So I think for our current implementation, by default, we use a track IK implementation, but that's interchangeable with any other IK as you like. Then, as Benny also presented in the last slide, we have in the last presentation, we have the speed scaling controller, which we developed for the ROS driver almost 2 years ago now. And recently we've been refactoring this out of your robot driver so that it can be used with other robot drivers more easily. So it's a standalone package, standalone repository. However, in principle, it's nothing has changed very much there. So the motivation was that many industrial robots actually provide some kind of speed scaling mechanism so that you can set the speed on the teach panel, for example, or as it was mentioned recently as well, that the robot automatically might scale down due to some safety restrictions or maybe just some settings on the controller where there's a maximum speed set. And if we're not aware of this on ROS and we command faster speeds, then it actually will get slowed down. And if we're not aware of that on the ROS side, then things get wrong in some way. So that the trajectory is not finished when ROS expected to be finished. Stuff like that. And we wanted to prevent that basically to make ROS aware of the actual execution speed. And what is really nice about that, what you get for free basically, is that if the robot completely stops, like for example, with an EM stop or a safeguard stop or whatever, at least for UR robots, then that's kind of similar to a speed scaling set to 0. So the trajectory will get paused in that case. So for example, as you've seen in the down video there, the video at the below, if there's a laser scanner which is connected to the safeguard output, it pauses the robot, and as soon as the field is left again, the robot just continues with the motion, and that all happens transparently for ROS, so that the interface is not destroyed because the trajectory takes longer than expected. The integration is kind of the same as for the other controllers that I mentioned. You just have to add the scaled interface and the scaled joint handle, and then that can be used together with the scaled joint trajectory controller, which was briefly introduced by Benny in the presentation before, so I don't have to do that at that point, so thank you for that. And the other things basically stay the same, and we have the scaled joint trajectory controller, and the other controllers that we have, like the Cartesian trajectory controller and the path-through controllers, also get scaled and use that mechanism automatically. Or the path-through control, basically, they do that by default for the execution time as well. But on ROS side, we also subscribe to the speed scaling so that we are still aware of whether the trajectory should have been finished or not correctly. So for the future work for these ROS control extensions, we'd hope that things get adopted by the community, and I'm very happy to see that actually people are using the scaled trajectory controller for their purposes, not necessarily with the purpose that we had in mind, but it's nice that other people see different applications for that, so I'm really happy about to see that. Would be nice if other ROS drivers would incorporate some of the new features into their drivers as well. And I'm actually planning on trying to get the speed scaling interface and the scale controller maybe to the default set of ROS controllers to make that more accessible for everyone. Some of those features are already ported to ROS2, like the speed scaling is available in the ROS2 driver as well, but some of the other concepts still need porting to ROS2 as well, which is on our schedule. At this point, I'd like to hand over to Rune, and he'll tell you a bit more about the other things we did in our project.
Yeah, hello. So we also would like to invite the ROS stuff more into our ecosystem as well. So we have facilitated this ROS as a service URCAP, which makes it possible to actually get published information into our UR program. So here's a simple animation here where we show that you can interface with the turtle tutorial, set it through the URCAP, select a node to the program tree and add additional parameters and publish that to the topic. So what we have so far on that perspective is that it can publish a message to a topic, read a message from a topic, call a ROS service, and trigger an action. The whole thing is based on the ROS bridge. So in the robot control program, we compile a JSON script, a string, and send it to the ROS bridge, and we are doing it through that. Yeah, interesting to see what can be done with this component here, and we really would love to see some inputs to how to improve on this perspective. But also just to highlight that actually our platform is quite flexible, and it can also be used for the ROS community. Then, as mentioned here by Felix, but also at the ROS World, we have I would say, a release candidate available with basic features for ROS2, done mainly by Picnic, but also together with FZI and us. And actually, I think we received a lot of feedback already, and please continue. And as with the ROS1 driver, it supports CP3 as well as the E-series. Have this joint speed scaling interface as well as the joint trajectory interface. Velocity was not yet implemented as far as I'm understanding due to the ROS2 control, but I guess it will come at some point. So yeah, and thanks for Picnic, of course, a great integration with MoveIt. Great stuff there. I will suggest looking into the ROS World presentation. I hope it will be online soon, where Dennis was presenting the driver as well. So great stuff, and a lot of features is already in. Yeah. Future work, and I actually would like to highlight some, at least the direction we would like to go. So of course, for industrial purpose, robustness is just a very big thing, and it doesn't really matter how many features you have if you don't have the robustness for the use. It's not really have any meaning. So robustness and easy of use / maybe easy get started as well. Yeah. So a bit more structured highlighting here. So reducing the real-time requirements for the host of the driver, I think it's could be very beneficial. So moving a bit more stuff to the controller, your controller. There have also been some good inputs regarding disconnecting, network challenges. How can the driver be robust to that, and improve the get started documentation. Examples of, as well as binary releases could help in that regard. Also some great inputs regarding how to integrate more stuff into the ROS ecosystem and UI ecosystem together. So the UI robot have this safety system, including some safety planes, joint limits, stopping time, and so on in our safety settings. So why not distribute that information for a planner, for example, that can take that into account. Then actually I have a better question, and I would like to get some feedback of what about Windows support? Will that be beneficial, and kind of when and why and where? And I've seen that some is trying to use the subsystem for Linux on Windows. And how well does that work? I will really be keen to hear about that. Yeah. And then our last slide here, I would like to acknowledge the community actually, because you have helped with a lot of feedback and driving this driver forward, as well as we in the past forked the modern driver. So thanks for that contribution, and please continue giving us feedback. Also good feedback would be nice, not only bad, but issues is very appreciated, as well as pull requests and suggestions. So yeah, thank you.